So this is a little bit of how we got here in terms of space missions, is that really you can trace the history of rocketry, at least the modern one. Certainly there are evidence of like fireworks and things like that that date back to you know, medieval China. But the first person who really started proposing rockets as a form of getting off of planet Earth and into space, which it must be so. You really can't have an airplane if there's no air, was Robert Goddard. There's a Space Flight Center in Maryland, which is named after him. He really was one of the pioneers. And this is kind of what you would call a hobbyist, somebody who just kind of was doing this on their own accord. This is one of Robert Goddard's rockets, so that's the body of the rocket. You can buy something equivalent to this in any hobby store at current times because of what we know about the chemistry of making rocket propellant. This kind of languished as an eccentric idea until the middle of the 20th century, when a different group of people with a very different purpose started getting very serious about rocket engineering. Anybody know what this artifact is? Yeah, it's the first of all of them with its very distinctive paint job. So this is this weird bunker area in northern Holland called Peenemünde, where the German rocket engineers made these things. And this is the infamous V2 rocket. It's totally like the Bugs Bunny style, go to the moon rocket. And they made these things to shoot them at London because all their planes were getting shot down. So unfortunately, that was the German army did some pretty good work, for better or worse, on rocketry. At the end of the Second World War, there was a race in between the Soviets and the Americans to see who could collect as many rocket scientists from the German army as possible and whisk them back to their home countries, seeing the obvious utility in things like this, where you can just kind of strike at your enemy with impunity. So absolutely not like scientific. And within 30 years, so this is the V2 rocket, this is a human for scale, about the width of my pinky. And within 30 years, this is the Saturn V rocket, and that's the size of a human. So all relative to scale. Okay, so you should stop for a moment and savor the fact that we convinced people, and they're very happy to do it, to elevator to the top of this, sit in this capsule. This is a silo of explosive gas, liquid oxygen. We shot them to the moon, and they were basically okay with that. Also, for those of you who suffer from exam anxiety, a person's heart rate never got above like 80 beats per minute. Why is that? They were not drugged into submission. Because every day they put the Apollo astronauts in a room that looked exactly like the capsule chamber, and they made loud noises, and they shook it, and basically simulated the launch to the point where they were totally conditioned away. And it was true for the animals, the Russian dog Laika and the American chimp, I forget his name, that they sent up into space first, is they just conditioned it away. So you do something every single day, and after a while, like, your anxiety response is gone. So you should sit every day at your kitchen table with no music and take math exams if you have math phobia. So under other circumstances, you would take people who built machines to bomb neighboring countries and their civilian population and put them in front of war crimes tribunals, but these guys got a pass because they did this for some reason. Then the space race was on. I just want to indicate that it wasn't really like smooth sailing. So really the first kind of political shot was in October of 1957 when the Russians got something into Earth orbit, so Sputnik 1. And Sputnik is a ball about yay big with 4 metal prongs coming off of it, and it just sat there and kind of like beeped with a radio transmitter, and it orbited. In 1958, the United States separated off. So the stuff previously had been part of the Army Air Corps, later the Air Force. So a civilian space agency was made in 1958. So at the end of the course, when I talk about how much money NASA has spent over its entire career, that's really like half a century of NASA funding. So got into lunar orbit, the Russians in 1959. In 1959, the Americans got into solar orbit. It's not what they intended on doing. They were trying to get into lunar orbit and missed and ended up orbiting the sun. Basically, if you miss, you always end up orbiting the sun. So, sort of a backhanded compliment of an achievement. This is not as easy as it sounds. And this is the early history of some of the failures. So in 2 years, Pioneer 0 blew up on the launch pad. They blew it up because it was malfunctioning. Pioneer 1 was supposed to go into lunar orbit, missed the moon. Pioneer 2, engine failed as it was coming up. I think it crashed in the ocean. They stopped numbering them sequentially at that point because it started getting embarrassing. Pioneer P1 was supposed to have like a probe that separated. It did get into space, but then the probe just shot off to nowhere. Pioneer P3, probe launcher malfunction. Pioneer P30, missed lunar orbit. And then we started convincing people that they should ride on these. So Pioneer P31, so now numbers are getting silly, probe got lost again. Fast forward a little bit, yeah, we put people on them, but this is really, like, as far as this class is concerned, the big achievement. And the big achievement is because of the power sources, or I would say at least, because of the power sources, the Pioneer and Voyager programs, is that it turned out that there was this alignment of the outer planets. So you see Jupiter, Saturn, Uranus, Neptune. And if you think of them as hands of this weird solar system cosmic clock, where Neptune goes around once every 84 years or so, and Saturn once every 30 years, and Jupiter once every 10 years, is that you're actually really lucky that they're in this nice kind of almost Fibonacci arcing spiral. So generically, what will happen is in about 50 years, like they kind of are now, is that Neptune might be here, and Uranus might be there, and Saturn might be there, and Jupiter might be there. That would be really difficult to go and take a grand tour of all of the outer planets at once. So people realized that this alignment was very fortunate and would not happen for some centuries to come. So there was a big push to send something and take a grand tour of it. So these were actually the real push behind the Voyager programs. And that's why we don't do this now. So we have these kind of single-purpose things. You go out to Saturn, you go out to Pluto in the case of New Horizons. We don't get to do this grand tour. This is after, within a couple of decades, a decade and a half of all the spectacular failures. The reason why this is such a success is not because, this thing actually made it off the launch pad, but also because what's powering Voyager 1 and 2? They're actually still sending signals back to us. No solar panels. Sun's pretty weak where it is now. Yeah, it's got a battery, and that battery is about 70 kilograms of radioactive material. And as the radioactive material decays, it creates heat, and the heat is converted into electricity. So it's a radiothermal generator. You guys actually saw The Martian. That was one of the accurate things, the crazy thing that he digs up. You have to be pretty sure of yourself if you're going to strap 70 kilograms of radioactive material on top of a rocket. Basically, that's like an intercontinental ballistic missile. So you really want to make sure that this works. So they got it figured out. They sent the rocket off. Voyager 1 and 2 did their grand tour. This spacecraft is about the size of this table, a little bit bigger with the dish. But the body of the spacecraft is not that big. Think back to the grapefruit model and imagine that you're passing by the small marble that is Saturn, the large marble that is Jupiter, and the two pencil erasers that are Uranus and Neptune. And they're separated by like 5 football fields or so. And you launch this thing off of Earth, which is the size of a pinhead. So imagine that you threw a piece of thread, leaves your hand, you don't really get to control it, and you make it through the eye of 4 needles. That's actually less of a incredible achievement than this is. So Newton's laws work really, really well. And somebody kind of, took the entire populace of the world's permission to launch a lot of radioactive material up into space. The famous icon from the Pioneer plaques, the ones that came before the Voyagers that were kind of a warm-up, are these. There's actually a lot of astronomy on here that we haven't covered yet. The idea behind this, and I don't know why you would do this necessarily. I don't think that it's a wise idea to tell aliens where we live. But this is the size of the Pioneer dish. These are humans for scale. We come in 2 flavors. This is a depiction of our solar system out to a planet that doesn't exist anymore, so they'll never find us. And then there's this kind of weird cryptic thing with all these dashes. Any guesses about what that is? Why on earth you would include this thing? Yeah, this is a hard question. So how do you tell people who don't speak your language, maybe no language, in like a universal description, how do you indicate where the solar system is? Yeah, so a lot of people thought a lot about this, and this is an attempt to indicate that the frequency, the fundamental unit they're talking about is the frequency, the vibrational frequency of hydrogen gas, because there's a lot of hydrogen gas in the universe. And these things are pulsars. So they're neutron stars that are rotating, which we haven't gotten to yet. And these are their frequencies etched in terms of multiples of the frequency of molecular hydrogen. And basically these pulsars spin around at their own frequency, and it's kind of like a bunch of lighthouses in the cosmos. And they're saying if you triangulate off of these lighthouses, you can find the solar system, and then you count in by 8 planets, 7 planets, and then find us. Right? Then they also, for some reason, included, I don't know, this is kind of charming. This is like PR thing. So there's this golden record with the sounds of Earth. So it's like some, all of the space agencies that contributed got to have a track on there. I think J.S. Bach is on there like 2 or 3 times, I guess. Germany, and then Canada was like, we have no culture of our own, so we'll just have Glenn Gould playing some Bach. And these are instructions in the same universal multiple of pi prime number coordinate system on how to make a record player. It was 1970, so that was state of the art, and how it might work. So you want to listen to this. Again, the idea of this being intercepted and played by friendly aliens is really small, but it's actually kind of I don't know. It's a nice idea that it exists, I guess. This is the real scientific payload. And so think about how people were taking pictures in 1972 when, these things were having their final engineering tests, or 1969 even. So this thing can't take pictures, send the film back, and have it developed, right? So really a lot of the engineering that went into the photographic systems set the basis for how a lot of stuff is done even today. So in fact, this is kind of, their solution was to have a magnetic reel that's kind of like a VHS tape, and the magnetic reel comes by and things get recorded on it and then read and transcribed to radio signals, and the radio signals get beamed back. So pixel by pixel by pixel by pixel. So in a sense, this is a start of what you might call digital photography, the idea of breaking things up into pixelation. Again, this thing got thrown off into the cosmos, and then 5 years later, so it comes and does this close flyby with some of the Galilean moons in the foreground. There's a nice, you can see the pixelation, picture of the Great Red Spot and some of the weather. And before this, ground-based telescopic observation wouldn't have indicated any of the really fine detail on the Jovian weather. But then there was this. So the big surprises were the Jovian moons. So the idea of these cryovolcanoes, these mixtures of ice and lava, as Io gets played like an accordion by Jupiter's tidal forces being ripped out. That was kind of a surprise. Saturn, there's the atmosphere of Titan, which was also a surprise. The fact that two of Saturn's moons had kind of funny reflective properties had been known, but the fact that it has an atmosphere was surprising. There's far side of Neptune, there's Miranda, the smaller Neptunian moon, and the very funny one. And then at this point, you can actually see the depth, so you can actually see that this white cloud layer is much, much higher than the methane cloud layer. And then what's that, actually? Yeah, it's a famous picture, isn't it? So that's Earth, yeah. That's Earth from 7 trillion miles away. And I think, I don't know, it's 6 by 6 pixels or something like that. And for a lot of people, there's something that astronomers kind of note called the overview effect, where they just have trouble getting pissed off about stuff after they come back from space. And some people hope that this would kind of ignite the entire planet Earth to do the same, is that all of the stuff that's annoying you and all of the international squabbles are going on in this 6 pixel by 6 pixel blob, and it seems a little bit frivolous from Voyager's perspective. Now at the time, this is in the depths of the Cold War, where basically half of Earth was threatening the other half of Earth, and vice versa with nuclear Armageddon on any given day. So good news is it worked, and we didn't have that thing blow up and scatter hundreds of pounds of radioactive material in the upper atmosphere and quash all further space travel. So we don't get any more grand tours just because of the planetary alignment is not as good as it was back then. But these missions, Juno to Jupiter. Cassini's been hanging out doing a great job around Saturn for a long time. New Horizons did its flyby of Pluto, which is kind of exciting. And then Galileo to Jupiter as well. So some of these, I mean, it's just worth watching and seeing, for one thing, the upgrade in the graphics, and secondly, some of the stuff that this is not like official NASA release. So NASA is a public agency, is required to release all of their data about everything, like exoplanets, whatever, into the public domain. So what you can do is download it and do science or non-science, and I don't know. So you could call these like fan vids, I guess. It's pretty reasonable. I kind of like the soundtrack on this one. So these are Cassini videos. Remember, this is like 40 or 100 meters thick. It's incredibly thin. So there's the ring shadows passing over the moon. And here is one of Io's eruptions. So this is a volcanic plume, which is some mixture of ice and lava. And again, the whole moon, Io is about the size of our moon, so the height of that thing is, like the entire size of Washington State. So why are these things so freakishly big compared to volcanic eruptions on Earth, now that you guys have finished exercise 4? Exactly, yeah. So the gravity on the surface of Io is much less than Earth, so our volcanic plumes are not 500 kilometers high. So it's not the worst thing ever. And then this one is nice because this was somebody who, I think the soundtrack is sort of ridiculous, but whatever. But this person did such a good job by taking Cassini mission pictures and just weaving them together. So not a trace of digital touching up or anything. These are actually, this is Saturn, and this is from the Cassini fly-through. That they actually made an IMAX movie out of this, and it was playing for a while. This is perfect. This is a Photoshop. And this is not a a collage Photoshop. It's actually Cassini images. I missed the Death Star. Yep. Yeah, you need, in order to get something that insanely uniform as Saturn's rings, is you need two things. Is you need like a really big central lump of gravity. So Saturn itself has a really strong gravitational pull. And then secondly, you need some sort of like damping. So it doesn't happen really quickly, and as you can see, Cassini passed through it without blowing up. So that stuff, it's almost like snow. It's really, remember, ice geology, not rock geology. You also need to have some damping, where if there was like a bubble in the ring or something like that. So sometimes it would be above the ring, some material, and then it would plunge down because of the pull of Saturn, and kind of like uh, a horse on a carousel or something like that. And every time it plunges through above or below the ring, what it would have to do is it would have to like bump into stuff in the ring. So every time it goes down, interacts with the ring, up, interacts with the ring, and eventually that damps out the ring so that it's like this incredible, thin aspect ratio. It is like 100 meters thick and 250,000 kilometers across. It's like pretty nutty, right? The ring itself? That takes millions of years. So that's actually more of a theory, but it's a theory that just relies on some pretty basic like Newtonian physics. So it's nothing like exotic about it. Yes. Yeah. So why does Jupiter win the weather war? So Saturn actually has some interesting weather, but part of it is that the cloud layers on Jupiter are compositionally distinct. So it's got the white from methane and water, and it's got the kind of like tan color from ammonium hydrosulfite and stuff like that. Then it's got the darker red stuff, which is some other compound, I forget which. But it's got like all three, so the weather looks more distinct. And Saturn just has the two cloud layers. So there's actually like very violent weather on Saturn too. If you were to hang out on the surface, it would be like trying to fly in a jumbo jet with no windows. And it's like hundreds of kilometers per hour of winds. It's just the color isn't quite the same. And there are storms and vortices on Saturn, much as there are on Jupiter. Nothing like the Great Red Spot. I don't think that has a full explanation. But there's equally strong weather on Saturn, just it's less colorful because of the chemical composition. And in fact, if you go to the north and south poles, there are all these weird vortices that form there that honestly are on par with the Great Red Spot. So, yeah, just not as pretty. I don't know. Yeah, good. Other questions? Okay. So yeah, flyby of Europa with its weird pressure ridges, and then final flyby of Uranus or cryovolcanoes. It's just some space porn. So for physics people, the real neat thing is we marvel about how give ourselves a pat on the back about how awesome Newton's laws work. And there was a thing for a while called the Pioneer anomaly, where one of the Pioneer program missions seemed to go too fast, and everybody got really excited because it seemed like Newton's laws weren't working. Like the Pioneer spacecraft was not emitting, didn't have any forces on it, it wasn't firing any thrusters, but it was like going too fast. And if something goes a little bit too fast with a little acceleration, that doesn't seem like much, but over time, if you guys have been through physics, like the distance grows like time squared if you have a little bit of acceleration. So this thing was like actually kind of careening out of control, and the distance was growing a little bit too fast. And so people thought that maybe like Newton's gravity only works inside of our solar system, and something new and exotic happened outside, but that was resolved. So Newton's laws work really well as far as the edge of our solar system. So we verified that by literally sending a machine exactly the way that Newton's laws would have predicted. So Voyager 1, as of, I guess, 3 years ago, 2.5 years ago, is now the first man-made object to get outside of the solar system by not arbitrary, but kind of reasonable definition about what the boundary of the solar system is. And we don't do it by some sort of material. You don't say like hyperbelt is the limit. It has to do with this bubble of material that the sun is puffing out. So something called the heliopause. And at the edge of that, apparently you get from a solar system environment, which is totally driven by solar winds. And then beyond that, you're actually in interstellar space. So the things that you see in terms of electric and magnetic fields and the particles that come in and interact with the spacecraft are totally different at the edge of this boundary. And there are all these weird kind of like shrieking magnetic anomalies that this thing is picking up and reporting back. So it's officially an interstellar space. So the human race has gotten something out of its one and only one thing out of the solar system. And despite the fact that it's from the 1970s, it actually has a Twitter feed, so you can follow Voyager 1 on Twitter. It tells you about things that it's doing. So right there, the termination shock at the end of the bubble that the sun is poking up. And eventually it'll get out into here, not during our lifetimes, but this kind of scary part of interstellar space. So likewise for Pioneer 10 and 11. So they do have enough speed to get out of the pull of the sun's gravity. It's this. So the heliopause is there. It's really hard to explain, but at the end of class, or in fact right now, if you guys want to crowd around, I can show you what the heliopause is in the sink right there. Because it's something that you guys have seen a million times every time you've like turned on the tap of a sink, but you never really thought too much about it probably, is that if you have material flowing off of something, there's a point at which the material slows down and starts kind of like interacting and sticking to itself as opposed to just flying apart. And there's a bubble that looks like this. So it's hard to describe. I could just like show you actually right now, unless anybody has any questions. Yeah, there's a primary part of the bubble, and then there's a trail behind it. So if you imagine the sun as like a train kind of like motoring its way around the center of the galaxy, it's actually like leaving, like a train does, it leaves a trail of smoke behind it. So our sun actually leaves this trail of cosmic rays and particles and stuff behind it. But then there's the bubble, and the bubble is the stuff that the sun is actively puffing out. And that's the heliopause. So now's good enough. Do you guys want to see this? I know it's like kind of cheesy demo, but this is, this is literally what the thing is. So every time you turn on a sink, you see this. So the water's moving really fast, and at some point the water slows down enough so that the water sticks to other water. This would be like the heliosphere, and this would be the termination shock and the heliopause. So imagine our sun's doing that with like material that it's ejecting, and at some point it slows down enough that it just kind of like starts hanging out and interacting with itself. And everything does this. So if you have material flowing off of anything in a source, it'll make some sort of structure like that. Yeah. I know that's like totally overwhelming as a demo, but like, that's really what it is. Okay.